lecture. Any questions while I get the lecture? All right, so we'll finish up everything mTOR today, the last of our mTOR lectures. We haven't really been talking about, other than answering questions, we haven't really been talking about what to do, exercise, prescription. We haven't really talked about this stuff. We've just been talking about physiology, whether it's biomechanics or straight muscle phys, size principle, things like that. mTOR and inflammatory physiology. But as we kind of come together at the end, you want to be able to use that information in a prescriptive way, in an effective prescriptive way. And so, well, let's just begin here. Just again, need, nutrition, assumption of nutrition, but really need and nutrition. Those are the two big ones that you can just override the system a little bit. But need and nutrition, that's really what's turning on mTOR. Now, as we talk about supplements, as we talk about drugs and supplements and ways of interacting with mTOR, we know about phosphodiesterase, PDE, right? It breaks down your cyclic AMP, it converts it into AMP, and AMP doesn't activate PKA. So there's like caffeine. We all have caffeine probably on a daily basis. Theophylline, this it's in cocoa, it's in a tiny bit is in like brewed tea, but it's a drug. It's a prescribed drug, theophylline. And theobromine, that's also in chocolate, these methylxanthines, and they're phosphodiesterase inhibitors. And so if you take a PDE inhibitor, you are able to activate more PKA because you are inhibiting the breakdown of cyclic AMP. So more cyclic AMP builds up, and the more cyclic AMP you have building up, the more PKA you're activating. And what does PKA do? Well, you're mobilizing fats, right? If it's PDE3B that you're inhibiting, right? You're mobilizing fats, you're doing more lipolysis. And so caffeine and chocolate and whatever drugs, PDE inhibitor, methylxanthines, these are effective at performance in sort of an aerobic situation, and maybe performance anaerobically too for attention, things like that. Inhibiting adenosine binding in your head. So there are some other effects of caffeine, but the mobilization of energy substrates, very effective, but it doesn't seem to impair muscle responses. So it's not like you take a bunch of caffeine as a pre-workout, and then because you're activating a bunch of PKA and mobilizing energy substrates, catabolism, you're breaking down fat and carbs, if it's in the liver, it doesn't seem to impair anabolic signaling really at the same time. So it's a nice effect. The PDE inhibitors, phosphodiesterase inhibitors. And you know what to do with amino acids. We spent a lot of time talking about this. Leucine is probably the most important. Arginine would be the second most important. And then you get into things like lysine, methionine. You get into some of these other amino acids that you do have cellular sensors for. You do detect when these things are coming in, but you can manipulate the system a little bit. You can set off the I have protein coming in alarm without eating whole proteins. Remember, about 90% of activation can be achieved with just leucine, lysine, and arginine. You don't need all 20, right? You can just pick a few, as long as you pick the correct few of these. And so this was an example of the effect of leucine, this study down here, the effect of leucine, where they had trained males, and during cycling, they look at these two different compositions of leucine, about double. So they have 3.5 grams and 1.87 grams, and they looked at protein synthesis between these two groups. And the higher leucine group had more protein synthesis. So leucine matters. They weren't even lumping it in with the others. It was just, let's give them a little more leucine. And so leucine is an effective amino acid, but you might as well use what you know, employ the information that you have. And so HMB, hydroxymethylbutyrate, it's a supplement that's been around for a really long time. It was never huge in the way that, like, creatine and some other supplements had this phase of being huge. HMB has sort of been beneath the serious popularity radar for a long time, but it works. About 5% or so, give or take, of your leucine is endogenously converted to HMB. It's a derivative of leucine. HMB is, and it's effective too, and it works differently. It works similarly but differently. And there seems to be some stimulation of protein synthesis, not as effective as leucine. It's not quite as good at leucine at stimulating protein synthesis, but the anti-catabolic effect does seem to be a little bit more. Um, that's really what HMB does well. Now, leucine does this too. Leucine is anti-catabolic as well, but there's evidence of um, the conditions, the scenario, the environment in which HMB is most effective, have people go into bed rest. Like if you're injured, let's say you're an athlete and you get injured and you're going to be bedridden for a while, or you just can't exercise or something. All right, throw in some HMB for a little bit. So this was a placebo-controlled trial over 10 days, and people received either a placebo or HMB, and they were confined to bed rest for 10 days. And this is lean body mass loss. The HMB group was able to preserve their lean body mass way better. P is 0.02. That's pretty compelling. So, there's a there's a if the null hypothesis is true, meaning HMB has nothing to do with the preservation of lean body mass, that would be the null hypothesis. If that were true, there's only a 2% chance you would have seen a difference this extreme or more extreme than that. So it's very compelling when you start looking at these placebo-controlled trials and the effect of HMB on preserving muscle tissue. And this is just sort of the numeric, the non-visual numeric look at, here's the control group and here's the HMB group, pre-bed rest, post-bed rest, and what the difference looks like in total body weight and body fat and fasted glucose, all this stuff. Now, if you're untrained and just initiating a resistance training program, you're just getting started, HMB might work in that situation too. It might ward off some of this initial catabolism, some of these metabolic cues that your body gets. Maybe, yeah, it might work in that situation. I'm not saying HMB is like a miracle supplement or anything. I mean, just leucine and HMB seem to work a little bit differently and how they're exerting their effect. Although one is a metabolite of the other, they are very similar. And really well-trained people, you just keep training, it's not really going to do much. I mean, if you're really well-trained and you're trying to get an edge, trying to improve your performance a little bit more, initiate a little more protein synthesis, I'll go with leucine, right? But if you're like, I'm just bedridden for a while, I sprained my body and I can't exercise, throw in some HMB for a little spell, and it's likely that you'll hang on to that tissue a little bit better. Also, if you're changing up your workout, if you're altering your workout in a novel way and exposing your tissues to novel stresses that are likely to be more destructive, likely to cause more damage, get more of an immune response, and garbage up some sarcolemmas a bit more. So at that point, HMB may have an effect as well of looking at that protein turnover, right? That balance between anabolism and catabolism, that overall metabolic point where you fall is are we favoring synthesis over degradation? Are we favoring degradation over synthesis? It depends on which side of that of that equation that you're modifying. You can just reduce degradation without really enhancing synthesis, and suddenly you're anabolic, right? If you just get rid of your catabolism, if you get rid of your breakdown. And that seems to be the role of HMB a little bit more. This is trimethylglycine, TMG, trimethylglycine, or betaine, right? Betaine, or trimethylglycine. And a methyl group is just a CH3. So there's just methylating stuff. Let's just methylate some stuff. And so that's what trimethylglycine is doing. But so this is out of Yukon. I know everybody except Brooke, I don't know, and Stewart, I don't know. The rest of the researchers on here, super good researchers. Jeffrey Anderson died like a year ago, something like that. He was the MD at Yukon for the basketball team. But really great research team here, and this was a placebo-controlled trial of looking at trimethylglycine or betaine, looking at this on mTOR signaling, and they did the study while I was there, and so I sort of watched this one unfold. And what they found was increased growth hormone. But yes, they found increased, PKB and increased mTOR and P70S6K signaling. But why? Why are they seeing this with trimethylglycine? It's like, well, there's more growth hormone. What does growth hormone do? Well, it makes you release more IGF. Well, let's check that. Oh, we're seeing more IGF. And the placebo group, we're not seeing that. We're not seeing more growth hormone in the placebo group. We're not seeing more IGF in the placebo group. And downstream from that, they're seeing more mTOR signaling. They're seeing more P70S6K phosphorylation in the trimethylglycine group compared to the placebo group. So often the way that I rank supplements is how much disposable income would I need before I do this one. I've never done trimethylglycine because if you have a six-figure salary, go for it. It's the same thing that I would say about, like, I don't know, carnitine and glutamine and these, like, oh, all right, if you have a six-figure salary, right? Now, leucine, are you making at least $30,000 a year? Go for leucine. Are you making at least $50,000 a year? All right, do H&B. Are you making at least $1 a year? Go for creatine. So, I mean, that's my ranking system of what's your annual income and is it worth doing the supplement? I've never done trimethylglycine, but if your goal is like, you know what, I just want to, without doing any, of course this is hormone altering, but sort of steroidal altering, sort of cholesterol hormone altering, without being picked up for, like, oh, you're an androgen user, avoiding that fate. If you just want to do supplements that people would consider, quote, natural, trimethylglycine, sure, incorporate that one with leucine and HMB. That's another one you can incorporate because there is evidence that it is going to work with mTOR signaling. Now, when you look at phosphatidylserine, this one seems to be effective for a lot of things. And most of the literature, we're looking at sort of older patients and cognitive effects, memory, things like that. When you get into the literature, you're seeing a lot of that. I take this one, but what it does is, in part, what it does is it tempers some of the spikes in cortisol. Now, cortisol has a lot of catabolic effects. Here's one with P70S6K inhibition. There's an article that talks about it, but this diagram is actually from this article. And so when you look at elevations in cortisol, we do have, yes, cortisol is a steroid hormone, adrenal cortex, the adrenal cortex steroid hormones come out of that. So it has its direct effects, but it also has, just like testosterone and estrogen, there are secondary effects of cortisol, very catabolic. Cortisol is very catabolic. You'll also see JAK-STAT inhibition with cortisol. I think STAT5, but there's probably a lot of points of interaction, and I'm less familiar with cortisol's relationship with JAK-STAT signaling. But you see reductions in growth. More cortisol means a reduction in growth, and phosphatidylserine is going to inhibit the spikes, the peaks of cortisol. It's not going to give you, like, Addison's disease, which means you have no cortisol, like Addison's, you have no cortisol. That's horrible. You do not want Addison's disease. That's a terrible thing to have. It's not like, well, I've eliminated my cortisol, so I am now a growth machine and I feel wonderful. That's not how it works. All things in regulation, whether it's in moderation, who cares? All things in regulation. and cortisol is one of them. If cortisol gets out of hand, you have Cushing syndrome. Not good, horrible, right? If you eliminate your cortisol, if you have no cortisol, you have Addison's disease. Horrible. Both of those are terrible. What you want to do is not have big spikes. You want to have managed cortisol. And so when you see this adrenocorticotropic hormone, you remember the hypothalamic pituitary whatever axes. So this is the hypothalamic pituitary adrenal axis. You get corticotropin releasing hormone out of the hypothalamus. You get to the pituitary and you get adrenocorticotropic hormone. And then you get to the adrenal glands, the adrenal cortex, and you release cortisol. And when you see this placebo-controlled trial, as phosphatidylserine, you have the placebo gets a big spike of adrenocorticotropic hormone. So this is the pituitary one. Now, probably this goes all the way up to the hypothalamus. When you take your phosphatidylserine, you're probably having a relationship at the hypothalamus, and because you see this axis being affected. Is that why you don't eat carbs? There's specific reasons I don't eat. There's a lot of reasons why I am on a ketogenic diet. We talk about that later. We'll get into my nutrition later if you want. But we see the placebo group, ACTH, adrenocorticotropic hormone, spiking, right? And then we see the phosphatidylserine at 50 milligrams, and then even lower, phosphatidylserine at 75 milligrams. So it's this dose dependent, and with nothing, we're getting this spike in what becomes cortisol, right? Because we see plasma cortisol levels. We see a similar relationship. The placebo group is having a spike in cortisol. And so phosphatidylserine, we see there's a bunch of effects. I mean, there's people doing 600 milligrams per day. I don't do that much. And looking at these differential effects on the endocrine system. And so in this study, what they did was 10 males, 5 are on a placebo, maltodextrin. It's like a really high glycemic carbohydrate that the FDA doesn't have a firm definition of, and so sometimes you will see fiber supplements are actually just maltodextrin. If you look at like oatmeal that has added fiber, they've just added maltodextrin to it, so it's just going to give you diabetes. I mean, it's worse than table sugar. Maltodextrin is in terms of it's the same thing that like if you're doing a marathon or something, and maltodextrin is a wonderful supplement to keep your blood sugar in check, right? To keep from getting hypoglycemic. Maltodextrin is wonderful, but there's a weird kind of FDA loophole in its definition. And so those I don't know, it's Palmer brand or something, those jams, if you go to the grocery store, which is probably super empty because of COVID, and you look at like high fiber jelly and high fiber oatmeal, and then you look at the actual ingredients, it's usually maltodextrin, which just means super high glycemic sugar. I mean, it's like super sugar, but people are pretending it's fiber. As soon as the FDA is not regulating very effectively, it's just people cheat. Just like in any sport, if you eliminate refs, people cheat. In the body, if you eliminate regulation, you're going to die pretty quickly. Without regulation in the body, you die pretty quickly. We need regulation in the government. People are like, oh, let's get rid of all regulation. Okay, we'll get rid of our country then. Regulation is critical at every step in biology and every step in everything from supplements clear to cellular functioning to sports and whatever. So 5 people do maltodextrin carbohydrate, and 5 people do phosphatidylserine, and then they collected blood values 30 minutes prior to exercise and immediately prior to exercise, and they do a bunch of cycling, intense cycling, and then look at blood values after. So the phosphatidylserine group, there's your cortisol levels. Placebo group, there's your cortisol level. So it really works. It's not just a one-off experiment that showed this. There are multiple experiments that show that this is a cortisol inhibitor. It is going to block spikes in cortisol. Now, it's not going to eliminate your cortisol, but it's going to put a ceiling on the spikes of how these things work. So that was the only statistically significant finding they had. But then you also see testosterone is a little bit higher, growth hormone was a little bit lower, but neither of those reached a level of statistical confidence where I would say, yeah, it does this thing. Maybe there's something there. Right? Maybe there's something there. So the placebo and phosphatidylserine for cortisol, yes, we see that. We see that in experiment after experiment. With testosterone, phosphatidylserine was higher, but not significant. Statistically not significant. And you can say the same thing with growth hormone, not significant. Lactate, there's no difference in lactate. And so cortisol really seems to be the big interaction with phosphatidylserine, and there's a lot of benefits can come from that, of tempering your spikes in cortisol. In part, cortisol is super catabolic, but also it's horrible for neurons. Your nerves hate that stuff. Yeah, maybe you'll focus on the immediate stress pretty effectively, but stress hormone, cortisol, steroid stress hormone. But good, when people talk about like I'm a bad test taker, okay, there's an actual physiological response here. If you get super stressed out for tests, you're getting a big cortisol response. Neurons hate that, so you can't recall information in the present. If the lion is charging you, just try to do multiplication tables. Good luck. Good luck. If you get super stressed out, good luck trying to recall things. So if you're a bad test taker, try phosphatidylserine. Just load up on that stuff. I mean, don't like take 50 grams, but like go take a modest dose, a couple 100 milligrams or something, and maybe that'll help. Maybe that will help. Or just study. When you're studying, get super stressed out, and specificity of adaptation, try to replicate that. Okay, arachidonic acid has some effect. This has been shown in literature to have some effect of arachidonic acid supplementation and human performance. And you know why? Cell signaling. So arachidonic acid, we are going to get our prostaglandins from. Now, I know people who have taken this. Thorin is one of them. If you're in athletics, you know Thorin Bradley. Or if you're a follower on his Instagram page, is like 1 billion followers. And he's done arachidonic acid, and I asked him, what does it feel like? He said, you just say you're so sore. You just get ridiculously sore when you're on this thing. You go to a workout and whatever normal soreness you would have. Now I just, I can barely walk when I'm done with this. And that's not really for me. I'm 40 years old, and I don't need aches and pains. I have like 3 herniated discs in my back. I just don't need additional pain in life. So but for other people who are just like, what, I will do anything to get big. I don't want to do, I'm being tested for androgens. And so I just want to do everything else that I can possibly do. Okay, sure. Throw in phosphatidylserine. Let's block some cortisol. Throw in some arachidonic acid, throw in some betaine, make sure you get your leucine, maybe a little HMB. All of these are pretty safe. Now, I don't know about the safety of overexpressions of this. This is the one out of all of those that I would say potentially there are some inflammatory complications of unbalancing this system to excess. But there is some evidence of if you're doing so we have a control group and we have an arachidonic acid group, and pre to post, when you look at like bench press and leg press, we're seeing these significant improvements on the Wingate, so power average and max power on the Wingate, and muscle protein synthesis comparable, whatever, but lean body mass significant only in the arachidonic acid group. There's some evidence that arachidonic acid works. Am I going to do it? No. Should you do it? I don't know. I would put this one at the bottom of the list, unless you just you need to do anything. You're an athlete and you have to perform to get a contract, or you have to perform to maintain a scholarship or whatever. Whatever. You know what to do. You have the information. You can make an educated decision, right? The important point there is that your decisions are educated, that you know how this stuff works, you know what it does, and what the effects might look like, both in terms of pros and cons, and for prostaglandin signaling. And also, if you're just really increasing your arachidonic acid and you have asthma, I don't know, maybe you get some leukotrienes, maybe, yeah, be smart. I'm just saying, be smart about this stuff. Real workouts over here. There are some serious workouts for the arachidonic acid or placebo. So this is Monday, Wednesday, Friday. Strength trained people. This isn't beginners. This is already strength trained people. I mean, they're doing leg press and bent over rows and lat pulls and barbell curls and military press and skull crushers. If you're saying skull crushers, then as opposed to like lying. Supine elbow extensions with, if you're calling them skull crushers, this is like somebody who's like a weight room junkie. Now, phosphatidic acid, you know what this does in terms of mechanical loading. So mechanical loading, diacylglycerol kinase, we're going to convert a diacylglycerol to phosphatidic acid. Now you can just eat it. You can just eat phosphatidic acid. That's fine. You can take that as pills. And it seems to work, but it seems to work in a slightly different way. Phosphatidic acid binds to mTOR. And this is one of the explanations of mechanical loading and how it turns on mTOR, how this mechanical activation of mTOR with phosphatidic acid. Now, if you eat it, you're going to convert a lot of it to lysophosphatidic acid, and you're going to get some MAPK signaling. So it's a little bit different. It's not this direct activation that you would have if you do this through mechanical loading, but you can eat it, and it does seem to work, but it seems to work through increased MAPK signaling. That's just what this stuff is talking about. It's the same article over and over. So endogenous PA, that's binding to mTOR. That's the mechanical loading stuff. Exogenous, you put it in your mouth, you swallow it, and you hope it gets to your tissues. That seems to be an MAPK. It's a little bit different. Lysophosphatidic acid, that conversion makes it a little bit different. But you do see improvements. This is phosphatidic acid compared to a placebo. And there's a statistically significant difference in improvement in total strength. When you're looking at it. Now, everybody's getting stronger, but there is a significant difference in the total strength of the subjects taking phosphatidic acid as a supplement. Now, catabolic supplements. These are good if you're a runner. These are good if you're an aerobic athlete, if you are a cyclist, a swimmer, a long distance runner, not like a sprint cyclist or a sprint swimmer, or obviously a sprint runner, but if you're a long distance one, AMPK is very valuable. You take a bunch of phosphatidic acid, get your lysophosphatidic acid, get your MAPK if you're a power athlete or if you want to grow or something. But if you're looking for endurance, it's not that helpful. What's helpful is AMPK, not MAPK. AMPK is going to be helpful for endurance. And well, how do you activate that? Oh, resveratrol is going to work a little bit. ICAR, AICAR, this one is prohibited, right? So when you talk about gene doping, the World Anti-Doping Code, talking about gene doping and ICAR. I don't like this idea of calling things gene doping, like you're modifying. When you look at what this stuff says, the use of agents that directly or indirectly affect functions known to influence performance by altering gene expression. Okay, so let's read that one more time. The use of agents that directly or indirectly alter gene expression. What does sugar do? Eat maltodextrin. That's the placebo. The placebo in these. Well, what does that do? Okay, well, you eat your maltodextrin, you get this is like a super high glycemic carbohydrate, so your blood sugar spikes. Your pancreas releases insulin binds to its receptor, the PI3K, PKB signaling, and then what happens there? You alter gene expression. Like turn on mTOR. What are you doing? You're altering gene expression. That's what you're doing with mTOR. And so there's nothing in the world that does. I mean, protein and sugar, a pancake. I'm not being like facetious here. I'm not exaggerating. A pancake alters your gene expression. And so this idea that the World Anti-Doping Code is banning things that indirectly alter gene expression, pancake, super, like very nearly directly. Now, directly, maybe we're talking like steroid supplement or steroid hormones or something like that. But like, this doesn't make any sense. So what ICAR is that is totally banned, it is an AMP, azine monophosphate mimetic. It's going to mimic AMP. So it's going to promote AMPK phosphorylation. Now, it's not doing the phosphorylation. It's an AMP mimetic. It is a sort of a surrogate for AMP to initiate AMPK. So yeah, maybe this could be stronger in this perspective than metformin or something like that. But I mean, just go on like a low carb diet and go exercise. I mean, that alters your gene expression. That probably works even better. So A lot of these things, when they get banned, just think like, why are we banning uh, androgens? All the arguments are bad. All the arguments don't make sense. And so you look at the World Doping Code, and this definition, according to this definition, waffles are you're banned from sport if you eat a waffle because that indirectly alters gene expression through insulin release. So ICAR, what is this doing? It is indirectly, is not directly, is indirectly uh, activating AMPK by mimicking AMP to promote phosphorylation by LKB1. And then what does AMPK do? Well, it's increasing mitochondrial biogenesis, and you know all of the stuff that AMPK is doing. It's good for aerobic activity. So there's just a bunch of weird information when you start encountering these things in the real world. If you know physiology, you sort of giggle a little bit, or you're like, oh, come on, like altering gene expression. This isn't CRISPR, right? This isn't like you're snipping up your DNA and replacing genes. You're just like it's all of this stuff is just gets a little bit nonsense when people don't know what they're talking about, and then they try to legislate based on a lack of information. Um, so we start with the premise that enzymes are trainable, um, and enzyme concentrations of all these things can be altered, whether it's PKB, it's AMPK, it's MAPK, it's mTOR, it's RSK. All of these different enzymes can be altered, and they're altered through behavior, they're altered through nutrition, they're altered through supplements and drugs. There's a lot of ways to modify all of these enzymes. And yeah, hormones do it. But people talk about hormones as this great thing of like, oh, this hormone. Really, the hormone is just affecting enzymes. There's a lot of ways to make these enzymes do the work. I don't know what to compare to. Like, hormones are maybe bossing people around a little bit, but they're not doing any labor. Hormones aren't doing the labor. Hormones are like the sort of ineffective boss. You have to have the employees do the labor. The boss isn't digging the ditch. The enzymes are digging the ditch. And there's a lot of ways to interact with those enzymes. So mTOR and adaptation, if you want hypertrophy, are you doing squats or are you doing single arm concentration curls? And remember the four upstream activators, promoters of mTOR signaling. We have chemicals, we have so immune system chemicals, we have nutrition, we have endocrine hormonal system, and we have mechanical loading. Now, if you activate more total tissue, you're going to get a more robust endocrine response. You're going to get more, especially if you start going heavy, think Henneman size principle, you're going to get more chemical damage, more tissue disruption and chemical damage. You're going to get more total mechanical activation. Everything but diet is enhanced here. This isn't doing all that much. You're stressing some particular motor nerves, but you're not really getting a big chemical or hormonal alteration there. And so you're missing some of those key inputs to activate mTOR. So lifting with multiple or at least huge muscle groups, what that's going to do. So think about when the forest fires were going. You can go outside now and breathe, and maybe you'll smell your neighbor's chimney fire. Maybe your neighbor's chimney fire. You can smell that one, sure. But if you're like in Los Angeles or Beijing, or you're anywhere in California a few months ago when the fires were roaring, you can barely breathe, right? It's like COVID. I'm wearing a mask for the forest fires. That is what you want for hormones and chemicals, because if you just go do concentration curls, you get this little effect. You get the chimney fire. You just walk down the street and you can't even smell it anymore, right? But if you're like California on fire, and Trump is telling us to, just make sure you run a rake through your forest. At this point, it's hard for that to dissipate without response. The chimney dissipates. The smoke doesn't linger. The forest fire, industrial pollution, this lingers. And it's the same thing in the body, where if you're doing a bunch of squats and pull-ups and all these big muscle groups set after set, high volume, lots of eccentric loading, you're getting Los Angeles. If you go and do all concentric activity, or especially like concentric concentration curls. That's the chimney. Then nobody cares. Nobody even notices. The tissue doesn't even notice that stuff. So you want these inputs, these higher threshold motor units, high volume, and the chemical response. Remember when we were in the uh, inflammatory, the healing and inflammatory section. And we were talking about the kitchen fire and how we heal. And the sort of the reason you don't want to take a bunch of anti-inflammatories and you don't want to get rid of this effect. You don't want to just go in and paint up the cabinets and pretend that's good enough. Those chemicals matter. Getting a big chemical response from exercise. Now, whether that's like, well, I exercised kind of lightly and I took a ton of arachidonic acid. All right, maybe. I don't know. It's not going to be the best way of doing it because you're not getting appropriate mechanical signaling. You're not using Henneman's size principle, electrically activating high threshold motor units. But okay, maybe you're getting a little bit of a chemical response that way, hijacking the system a little bit. But what you want to do is get tissue damage, a lot of tissue disruption, get IL-2, get IL-15. You're going to get some, TNF and some IL-6, which is a little bit frenemy like. And that's going to be a response for a lot of the hormonal stuff as well. But it's going to stimulate the hormonal response when you have a big chemical response. You don't want to abolish the chemicals. Now, mechanical loading, you know how this works. You know how mechanical loading works. Mostly integrins here, but there's a lot of mechanotransducers, these proteins that are going to transmit mechanical loads, and integrins are sort of the famous, well-studied, well-understood mechanical sensors, and that's extracellular matrix. And it's a transmembrane protein, so it relays that message inside using focal adhesion kinase, and that is going to elicit hypertrophy in a number of ways. But if a cell is not being activated, think Henneman's size principle, if a cell is not being activated, then like there's sort of no reason to make it adapt, right? It's not undergoing strain, right? It is not experiencing the load like the cell that is activated, the cell that is roaring through cross-bridge cycling and producing those mechanical forces and withstanding those loads put upon it. And so our cells know if they're being used, if they're contributing to a cause. Your cells know this stuff. And maybe there's a little bit of spillover. There can be a little overspill for the community fiber that wasn't really participating. Sure, yeah, but the bulk of responding fibers are the ones who are responsible for the production of that force. Now, the hormonal, the hypothalamic pituitary whatever axes, the hypothalamic pituitary adrenal axis. You can inhibit that one with phosphatidylserine. Right, so that one's going to be catabolic. If you're going to get corticotropin releasing hormone from your hypothalamus up here, and then just kind of south, the pituitary gland, right? You're going to get from the anterior pituitary, you're going to get your adrenocorticotropic hormone, and then the adrenal cortex. Cortisol is released from that, glucocorticoid, and then you're going to get inhibition of repair and regeneration and immune suppression and inhibition of mTOR signaling, P70SSK and your JAK-STAT inhibition. And so you're going to get a lot of protein degradation with cortisol. Okay, fine. That's hypothalamic pituitary adrenal axis, and you can inhibit that probably at the level of the hypothalamus. You can inhibit that with phosphatidylserine. There's other hypothalamic pituitary axes, right? So the hypothalamic pituitary liver axis. So that's the hypothalamus releases growth hormone, releasing hormone. And then the pituitary, again, we're in the anterior pituitary, releases growth hormone. And that downstream from that, we're getting the liver to release this IGF. And then IGF, we're getting a bunch of PI3K and some MAPK signaling for growth. The interaction with the tissue is largely mediated through IGF. The thyroid hormone, we're getting a lot of PI3K, PKB signaling there. Yes, the thyroid has a special circumstance where it can wiggle its way, be transported into the cell, and so it almost mimics the transport behavior of steroid hormones. The thyroid hormones are weird, but that's hypothalamic pituitary thyroid axis. There's a hypothalamic pituitary gonadal axis, and so if we're going to make testosterone That's the HPG axis. So the hypothalamus relays messages to the pituitary. The pituitary gets out into the periphery, sort of ease out in the periphery. So the hypothalamus is behind the blood-brain barrier. The pituitary is out into the wilds. In the like vanguard or the forefront or whatever. It's out there in the wilds, not protected by the blood-brain barrier. So the hypothalamus, and it's from its protected throne, sends messages to the general manager, which goes and instructs, the Dwights and Jims what to do, and who then go instruct all the enzymes how to do the work. A lot of steps. Nutrition. You know how nutrition works. Okay, carbohydrates. We're going to get an insulin response from carbohydrates. You know how insulin works. Binds to an insulin receptor. You get insulin receptor substrate, that protein, and PI3K to convert PIP2 into PIP3. Docking station providing PDK access to activate PKB, then PKB phosphorylates tuberin, and that prevents tuberin from facilitating the hydrolysis of Rebs GTP into GDP. So you know insulin signaling, you know how that works. But then also remember the beta subunits on AMPK. The beta subunits on AMPK, glycogen is going to bind there. So if you have a bunch of glycogen, you're going to inhibit, and the characteristics of glycogen, but that doesn't really matter. You're going to inhibit AMPK on that regulatory subunit, that regulatory beta subunit. So that's carbohydrates. That's your banana. That's why banana is anabolic. That's why banana would be banned according to the world anti-doping agencies' statements, and how the insulin is. I mean, that's it's indirect, but that's a pretty pronounced. A banana, a non-GMO banana, organic non-GMO banana is regulating gene expression. It is a major influencer of an indirect influencer of gene expression, both at the level of if you get a bunch of insulin binding. Now, insulin, PKB is going to initiate the mobilization of GLUT4 to call sugar in. It also turns on glycogen synthase. So you make more glycogen. So if you have insulin signaling, you make more glycogen, stored carbohydrates in the skeletal muscle. And when you make more glycogen, glycogen binds to the beta subunits on AMPK. And so with insulin, we are inhibiting AMPK very indirectly. We are promoting protein translation. So that's carbohydrates. Proteins, I guess that's carbohydrates too. Let's get into the proteins, a bunch of hot dogs and eggs. Proteins, as you know, this is the mobilization of mTOR to the work site. This is, let's shepherd the mTOR complex to its site of work. At home, it's unwilling to check emails. At home, it's unwilling to respond to answer phone calls. And at home, it's unwilling to dig ditches or whatever. Once it's at the work site, it clocks in. That's right. It goes to the lysosome and clocks in for work. That's what mTOR does. How do you get it there? Well, proteins, right? Well, the RAG, GTPases, but proteins are how mTOR migrates, how it translocates to the lysosome. Kind of off topic, but how much of an effect do artificial sweeteners have on insulin levels, if any? I've seen a lot of conflicting stuff out there, and I consume a lot of them. They seem to be fine for the most part. Artificial sweeteners. You look at, they don't really seem to have an effect. Now you get a huge dose of these things and particular ones, and you will see some insulin response a little bit, but most of them not really. With stevia and saccharin has been around since the 19th century. I mean, 1800, saccharin's been around. And there was a little scare with saccharin about bladder cancer, but really what that was in rats. And rats have this concentrated urine with different ion concentrations in it. And saccharin crystal, that's the sweet and low, the pink packets, the sweet and low ones, that's saccharin. And it crystallizes in a rat's bladder, and attaches to the bladder wall. And in humans, that doesn't happen. Like there's to my understanding, there's like never been a cancer case ever once connected to saccharin in the 100 and whatever 40 years that it is. I mean, this is the late 1800s. This thing came out. We've had a long time to study this, and um, the like equal packets aspartame, that's just a couple amino acids. It doesn't really do anything, uh, unless you have phenylketonuria. If you have phenylketonuria, that's bad. um, but nobody in this class has that. And like, eating fish would be poisonous to you if you did. Oh, but yeah, most of these artificial sweeteners. Now, some of them, when you look at, some of them have a little bit of, caloric content. When you look at something like, the sugar alcohols, I can't have those. I mean, that just like lubes up the like colon. It's like, man, if I have sugar alcohols, I'm just gonna like pissing out of my asshole for 2 days, and I can't touch those things. And so that's what a lot of people experience, is this, like, you just get this gastrointestinal discomfort, and like, oh, how many consecutive episodes of diarrhea can I have over the course of 3 days? So let me take some sugar alcohol and see. So I won't touch that stuff. um, but often you'll see sugar alcohol mixed in with it in a very small dose, of some of these things. But yeah, you don't really see an insulin response in most of these things, and it's sort of, it just appears to be fine. But keep an eye on the literature every few years, because the state of evidence today is not the state of evidence 50 years from now, and it's important to be updated on areas. And if you're, but I've never seen anything that says these, oh, like even the sugar alcohols, other than that side effect, or aspartame, other than if you have phenylketonuria. There's specific situations in which these things, people can react to them, but it doesn't really seem to have an insulin response. You don't I mean, you just sort of get rid of these things. So, but there may be, future evidence that contradicts what I'm saying today. So what I'm saying today is not eternally true. It's based on the state of evidence. Now, people get very passionate about this stuff. This was before, a long time ago, before I was ever a professor. I think I was a community college professor or something at the time, an instructor at a community college, and I was giving a presentation, to a bunch of, I think it was high school teachers, and this lady, I was talking about the state of evidence with artificial sweeteners. This lady stood up in the middle of my presentation, was like livid, and she's like, "How dare you?" So I'm like, "Well, I don't know. You can be as passionate as you want, but the data don't support you. It's I'm saying what the state of evidence is there's no like, I'm not profiting off of this. The people who are doing the research have no financial ties. There's no bias. It's just like, and so it doesn't seem to be, people sort of demonize a lot of these things that don't have any, demonic qualities to them that we know of. Now, sort of the end of all this, we're looking at two different activation pathways of mTOR: and amino acids, protein availability. This is lysosomal translocation of mTOR, of complex 1. Amino acids, we are moving mTOR to the lysosome so that it can work, so that it can interact with Reb. It's not going to interact with Reb if it's not at the lysosome. And I don't know where it was before. Where was mTOR before it got to the lysosome? I don't know. I tried to call it and it didn't pick up. And then so I put out a bunch of amino acids, and it showed right up, that. And so that's sort of the translocation. Who cares where it is out in the, cytoplasm, but it gets mobilized to the lysosome, given the introduction of amino acids via RAG GTPases, and with a particular interaction with Raptor. And so that is the rags to Raptor, and that mobilization, that's how it's going to get there to the lysosome, and that's where it's going to work. Now, that doesn't turn it on. That doesn't, having amino acids, that doesn't flip the on switch. That just delivers it to the place where the on switch lives. Growth factors are needed to actually turn it on. You can't just have one or the other. You flip on the on switch and there's nothing there. Again, like, you call it and it's not there. Amino acids, it shows up and there's like nothing there to do. Like there's no task. I don't have a to-do list. All right, fine. I'll just hang out here. I'll relax. I'll take a nap. And so you need both of these to turn on mTOR. Now, the growth factors, this can really come from a lot of things. It can come from insulin. You can just eat yourself into mTOR activation. Have a bunch of protein and carbohydrates. Have a well-balanced diet with meat that has sugar on it. Go for it. Um, you can do a bunch of exercise and get uh, cytokines and get some like prostaglandins and get some IGF and get this response, this exercise response, the interleukins and stuff. That's going to do PI3K and MAPK signaling. Okay, you could do that. So there's different ways to turn it on over here, but over here, really, you should be introducing amino acids. And what is mTOR actually doing? It is turning on protein translation, which is the linking together of amino acids. And it needs amino acids to do that. It needs the ingredients. So mTOR is not eager to begin synthesizing protein, translating protein, linking together amino acids, manufacturing these proteins. It's not eager to do that if it doesn't have the ingredients to do so. If it doesn't have the ingredients, it's not eager to do it. So you have to give it the ingredients, shows up to the worksite, and then you activate it. All right, let's go back to the first slide. This is the first slide I showed you when we got into mTOR. When we started the mTOR lecture, this was slide number 1. What is hypertrophy B? Now, what is hypertrophy? You should be able to answer all of these questions now, right? Our full circle has been completed. Our Krebs circle has been completed. We're back to oxaloacetate. We're back to slide number 1. And so, what is hypertrophy? Well, it's protein translation. Hypertrophy is manufacturing proteins in excess of degradation. It is synthesis outpacing degradation. Why does hypertrophy happen? Remember why questions. This is fitness. This is metabolic fitness. This is trying to optimize your tissues, your cells and your tissues to the environment and the stresses in which they live. What loads are they being subjected to? What stresses are they coping with? What is the inflammatory and mechanical environment in which they live? Let's try to calibrate ourselves to be perfectly fit to those circumstances. That's why hypertrophy happens, is there are environmental stresses and triggers and loads and conditions that the body is trying to become more optimized to flourish within, more optimized to tolerate without breaking, without risking harm, without injuring oneself, and to allow the performance that seems to be necessary in life because you keep subjecting yourself to this. That is why hypertrophy happens. How does hypertrophy happen? Well, mTOR mostly, not exclusively. Right? You know that these steroid hormones are going to have their sort of transcriptional direct effects. So testosterone. Let's bind to a little hunk of DNA. Okay, fine. The bulk of your protein regulation, your metabolism, the protein turnover, that balance, the bulk of that is going to be cell signaling cascades. Is going to be mTOR, and that's how this stuff is happening. And so it's the interpretation of upstream signals and the relaying downstream to P70, SSK, 4EBP1. So how is it happening? mTOR, and then the last thing that we talked about, sort of combining all of this stuff. What we just finished talking about is what supplements and how does the inflammation that we talked about earlier, where does that play in, and why are we not taking ibuprofen? What's bad about that? Like, why do athletic trainers and sort of sport coaches and even strength coaches sometimes, why is everyone on like NSAIDs? I mean, this is ridiculous. We are stealing from people's futures, stealing from their future health, stealing from their future performance to get them on the field today. I mean, it's a matter of biological theft to some degree. It's not a ridiculous uh, accusation to say that we are leveraging futures for today's performance. Like, this is just, it's terrible to be, it's like criminal to do this to people, and yet everyone's taking ibuprofen, vitamin I. Um, and so Henneman's size principle and the nature of loads that are going to elicit mTOR signaling, making sure the high threshold motor units are there, the characteristics of exercise, specificity of adaptation, and how that is going to uh, manifest in specificity of mechanotransduction, right? The load specific information that gets relayed. You can activate, you can do Henneman size principle, orderly recruitment size principle. You can activate those high threshold motor units with a low load using time, right? Because need is the big determinant of how Henneman's size principle works. So need sufficient. Yeah, but you're not really getting mTOR signaling if you're activating high threshold motor units using endurance parameters and endurance characteristics, or you're just holding on for a really long time. Eccentric loading, eccentric or eccentric loading, and how that works, the different interactions where that plays in, everything from stretch activated channels to integrins, to myostatin, to MGF, mechano growth factor, these different responses, prostaglandins, these different responses of eccentric loading, and how that is going to interact with mTOR. So all of the muscle physiology characteristics we've been talking about all semester, really where they play out, where those things elicit their effect, is in the map, right? They enter the map somewhere. They take an on-ramp onto the mTOR map somewhere. Now, is that with ion balances? Is it with at a cell surface receptor? Is it, what signaling cascade are we working with? Is it inhibition of a phosphorylation somewhere? Are we inhibiting the phosphorylation of like Raptor or P70S6K? What is the on ramp, or where do we put up the cones? Are we AMPK and we're inhibiting mTOR? Where do those cones go up? Where the road closed, right? Well, we're looking at detouring. We're putting a road closed sign at Raptor, and we're detouring traffic into tuberin. We're opening up tuberin, and so we're looking at these map manipulations, and all of the variables we've been talking about all semester are really can be found biochemically in mTOR, how they're having that effect. Okay, so some review slides. What enzyme stiff arms mTOR? AMPK. AMPK, arguably the most catabolic enzyme in the body. You could say PKA, maybe. Okay, whatever. So you could present an argument for these things. This isn't a debate class, and I really don't care what holds the title of the most catabolic enzyme. But AMPK, very worthy contender of that crown, of that aerobically fit, anabolically inhibitory crown. And as we know, the major sites, the two major ways that it's inhibiting mTOR is activating tuberin, which is deactivating Reb, which is breaking down, facilitating the hydrolysis of Reb's GTP, and GDP bound Reb, that's not activating mTOR. And activating or inhibiting Raptor. Raptor needs to recruit the downstream targets. Can't do that if you have phosphorylated it with AMPK. So why does AMPK do that? Remember, why is the sky blue stuff? Why does AMPK inhibit mTOR? It's looking at ways to save on the electric bill. AMPK is looking at ways to save ATP and increase your storage. It senses energy. Now that calcium calmodulin dependent kinase, right? You can also sense ions, stuff like that, and TAC1, TAK1. I don't know how the hell what conditions. I've never seen a journal article that really outlines what conditions that thing is an upstream activator of AMPK. But LKB1. LKB1, this is our primary activator, liver kinase B1. Again, don't think of it as a liver kinase. This is ubiquitous. This is all over the place. Just look outside and there it is. And LKB1 is going to activate AMPK in the presence of an energy deficit, in the presence of an altered ATP AMP ratio. The more AMP you have, the more likely that AMP is going to bind to the gamma subunit. The AMP is going to bind to the gamma subunit on AMPK. Now you get a couple of those to bind. The second one is going to bind much with greater affinity after the first one binds. And now we have opened up access for LKB1 to phosphorylate the alpha unit, to activate it. This is really the activating kinase is LKB1 in response to energy stress. And so AMPK is an energy sensor. AMPK senses that you're low on energy. ATP is low, AMP is high. Remember, ATP will inhibit the phosphorylation by LKB1. And AMP and ADP are both going to inhibit the dephosphorylation, so the deactivation. But AMPK is an energy sensor. When AMP levels are high, it is going to do whatever it can to save ATP and promote regeneration of ATP levels, both acutely and chronically. Now, acutely, let's shut off mTOR. Let's get some carbs into the cell. We will mobilize GLUT4, get some carbs into the cell. We'll activate hexokinase and PFK. Let's get those things to consume those carbohydrates to create more ATP. And again, in the hormone-sensitive lipase stuff gets a little bit tricky, but in the muscle, let's oxidize a bunch of fats, right? Let's be very catabolic with fats to generate a bunch of ATP. You don't need to know the whole story of fat, but just think of ATP or AMPK as doing whatever it can to generate ATP and to limit unnecessary expenses of ATP. Now, when we look at mechanisms of fatigue, which I'll talk about after Thanksgiving break, I'll talk about mechanisms of fatigue. There's arguments for cellular fatigue, there's arguments for central fatigue, but really what fatigue is doing is you don't want your brain to be denied fuel. If your brain is denied fuel, that is a life-threatening problem. It's okay for the periphery to be shy on fuel because you just sort of get like weak, you get fatigued and weak, and that's fine. If your brain is denied fuel, I mean, that's like a critical life-threatening scenario. So we have a lot of physiological steps to limit fatigue, to limit our overcompensation and I'll just muscle through this and see if I can exercise so hard that my brain is denied fuel. There's a lot of things to shut us down, and AMPK is this kind of early register of what is our energy status. What does our bank account look like? Are we getting down into overdraft fees section? We got to prevent overdraft fees, right? So that's why. That's the why. The how, right? The how, FOXO, ULK, ULK1. Let's turn on some protein degradation, but also let's just shut off mTOR, right? Maybe some direct interaction, but tuberin and raptor, these are these primary hubs of interaction. And let's stop mTOR from getting us downstream targets, and let's just stop mTOR from being activated at the tuberin step. Let's stop Reb from activating mTOR. So that's how AMPK shuts it down. It also AMPK chronically is going to increase mitochondrial density, right? Mitochondrial biogenesis. And so that's a more chronic effect. And as you know, in the hypothalamus, AMPK gives you the munchies. What day is it? Wednesday? I don't know. I doubt any of you have the munchies right now. But so that's how, if it's leptin or if it is cannabis, or how this stuff works, how the munchies manifest, or how satiety, the opposite of that, how that physiologically at the level of the hypothalamus, how that is going to play out. How does AMPK get activated? As you know, LKB1, that's the only one you need to know. LKB1, it can phosphorylate it at the alpha subunit, when in times of energy stress, in times when AMP, that ratio, when AMP to ATP ratio is high or ATP to AMP ratio is low, you get the idea. So there's AMPK. These are the alpha, beta, gamma subunits. Beta, right? That's where your carbohydrates, that's where your glycogen is going to bind to beta. Gamma, that's where your ATP, ADP, AMP, that's where those are going to bind. How do you eliminate AMP, not AMPK, but how do you eliminate AMP? There's an enzyme, AMP deaminase, right? You deamine your AMP deaminase, and you convert to IMP, inosine monophosphate, and ammonia. And that will come up later when we're talking about the mechanisms of fatigue. But how do you eliminate AMP to try to get your ratio back in order? Because that ratio is so critical. The ratio is so important. It's not just how much ATP is there and how much AMP do you have. It's the ratio of ATP and AMP that becomes so critical. And so how do you eliminate AMP to reestablish a performers ratio? You use AMP deaminase, and what is a drug that inhibits this, a medication that inhibits that? Metformin. Metformin is going to inhibit that. And so that's how metformin is going to increase the amount of activated AMPK. Activated AMPK is going to call sugar into the cell. It's going to get GLUT4 translocated. It's going to get sugar into the cell, and it's going to turn on hexokinase and PFK, phosphofructokinase, to burn that sugar that comes in. So as we get near the end of class, just know these questions. Go through these questions. We've talked about a lot of them today. Now you don't need to know names like Earl Wilbur Sutherland and Carl Corey. You don't need to know those names. That's just cyclic AMP, right? That's the second messenger that was discovered. A Nobel Prize accordingly won. And so that would be PKA signaling. And so catabolic, let's mobilize stuff like that. So anabolic versus catabolic hormones. The different classifications of hormones, amine or peptide, protein, where these are all made from strings of amino acids. So we just call them polypeptide or whatever. And versus steroid hormones made from cholesterol. GLUT4 translocation, what perilipin is. This guy over here is representing perilipin. What cell types are multinucleated? So the muscle is huge cell type. I mean, cancer too, but muscle, it needs a bunch of nucleuses, muscle nucleuses, myonuclei. And because you can only govern so large of a domain, you need to increase the number of nuclei you have before you can, transcribe and translate at a broader geographical range. You know what myostatin is? Follistatin is the binding protein. You're going to inactivate it. So this is technically anabolic, while that would be catabolic. You know what insulin-like growth factor is, where it comes from. The liver, mostly for its endocrine IGF. 98% of it or so is bound. Most of it to the binding protein 3. That also comes from the liver. These axes, HGH, right? Most of it, it has its JAK-STAT signaling, but most of the growth hormone, the human growth hormone effects are going to come from IGF. The hypothalamus, the hypothalamic pituitary thyroid axis would be this for T3, T4. And yes, they behave like steroid hormones in terms of getting into the cytoplasm, but there is PI3K, PKB, mTOR signaling that they're going to exert. They're going to work through I5 also, PKA and PKB, that difference. And what happens to the muscle during hypertrophy? Like some of these, again, why and how questions. What's the cell signaling cascade? You better know that by now. That's what we've been talking about for the past however many 7, 8 lectures, 10 lectures, something like that. During transduction, what generally activates or deactivates the intermediates, a lot of this is going to be phosphorylation. You're going to attach phosphates to things. Kinases, a kinase phosphorylates stuff. A kinase is going to do the phosphorylation. So that's what a lot of what you're going to do is attach a phosphate to something that changes its behavior. Now, it's not the only way. You can bind something to something, whether it's phosphatidic acid or Reb or whatever. Um, this isn't phosphorylation, but metabolism and the enzyme stuff. Know what an allosteric site is, what competitive inhibition, non-competitive. You can ignore mixed. Suicide, know that that's like aspirin, the irreversible. This is the irreversible one here. And so just know those. There was one lecture where I just blasted through them, but definitely rewatch that one. The different steroid stuff, anabolic, androgenic steroids, the liver, right? If you inject, you're going to bypass the liver. That first pass hepatic metabolism just goes into systemic circulation, and so stuff like pileosis hepatis, and which is rare anyway, but those blood-filled cysts on the liver, and but the thing that happens to everybody if you eat steroids, if you put them in your mouth and eat them, because it's a steroid hormone, it's made from cholesterol, you can eat it. If it's something like insulin or growth hormone or IGF, or there's a protein, so eggs taste better, you might as well just eat eggs. It's the same thing, you're just eating it, breaking down into its component parts, the amino acids. But if it's a steroid hormone, you actually can eat it, but then it goes straight to the liver before it gets into systemic circulation, and then you see liver problems. But the main manifestation of that is where you regulate your cholesterol, and so you see LDLs go up and HDLs go down. You can bypass that. Definitely be able to talk about specificity of adaptation, be able to talk about fitness, and metabolic fitness, and what fitness really looks like. And how fitness, just the idea of is something compatible with its environment? Can it thrive in its environmental situation? I was going to say environmental environment. Whatever, is it suitable? Is it, that's what fitness is. But you know how it works. You know how fitness works. It's like a bunch of cell signaling cascades. And just definitely know these cell signaling cascades. So, insulin versus a steroid hormone. Insulin has to bind to a cell surface receptor. Right? It's a protein. It's made out of amino acids. A steroid hormone can just go right through. Thyroid hormones, you know why those are weird. Insulin's main function, GLUT4 translocation, but it is very anabolic in a lot of ways. Let's also turn on glycogen synthase, and which AMPK shuts off, and let's do a bunch of protein anabolism. Insulin is very, very anabolic. So you know what M is. This is where you practice drawing, or at least have a good drawing for notes in front of you when you're taking the test, to know what lives in those drawings. Now, for the proteins, I don't think I'm going to ask about castor, cestrin. Gator, I might ask about Gator 1. This is the primary sensor for amino acids, and maybe I'll ask about that. But we have cytosolic sensors for leucine and arginine, and down here we're in the lysosome. We're sensing arginine there as well. And this seems to be where lysine is doing a lot of its cellular enhancement, is through that lysosomal sensing of arginine and the RAG translocation. So leucine and arginine are inhibiting inhibitors of mTOR translocation. So inhibiting inhibitors of translocation of mTOR to the lysosome. And that's probably the extent of what you would need to know. Now, it's in life, it's going to be good to know a little bit more than that, but I don't know, for the test, understanding in a very basic sense what the amino acids do is they provide the stuff that's preventing mTOR from getting to the work site. They withdraw that prevention. That's how a lot of things are going to work in the body, is withdrawing regulation, withdrawing prevention. And even stuff like you start exercising, and the neural adaptation at the beginning of exercise, you don't start growing right away. All you do is sort of withdraw some of the neural policing, and so you're able to be stronger without more protein accretion, deposition of proteins, and withdrawing some of the, whether it's Golgi tendon organ or gamma aminobutyric acid, GABA, if we sort of withdraw some inhibition. and that's what amino acids are doing. So we know all about AMPK, right? This is tons of AMPK stuff. Does cable dative maturity pupil, raising your hand? Definitely know that. Is your padding pool spherical piston woofer? I'll probably ask that. What apparatus selection officer? Honeydew melon? See, these are just gibberish. Placing juice strut runners, waterproof inflatable igloo. I'll definitely ask that question. So transcription, translation. I will probably not ask what those are, but you know what that is. Make your mRNA and then translate it, right? You create your menu, your recipe, and then you take it to the kitchen and cook up the dish. And so take it to the ribosome and cook up your protein. FAK, you know, that's downstream. That's the sort of relay runner for integrins, and mechanotransduction that is going to work through PI3K, PKB, and non-PI3K, PKB signaling. Prostaglandins, you know where those come from. Arachidonic acids, a PLA2, cyclooxygenase, we get our prostaglandins, you know where those come from, and you know where they have their effect. It's much of MAPK signaling when they bind to their receptors. No PKA signaling and PKB signaling. Endogenous and exogenous inhibitors for mTOR. Exogenous, you know, mammalian target of what? Rapamycin, right? That's not endogenous. And so there's stuff we can introduce those inhibitors. Wortmenin is a PI3K inhibitor. Rapamycin is an mTOR inhibitor through FKBP12. And so those would be exogenous inhibitors. Endogenous inhibitors would be things like myostatin and AMPK. I mean, these would be endogenous inhibitors. And during exercise, so yeah, I don't know, regulation of lipolysis. And so what is the lysosome and myostatin? Know those things. Ubiquitin proteasome system, right? The ubiquitin tags to degrade. And PKA, you know that, you know, PKA signaling. Aspirin, you know, that suicide inhibitor of cyclooxygenase. Epinephrine's mobilization of carbohydrates through protein kinase A. Just what cell signaling is, very basic. What is cell signaling? And here we have these phosphorylation cascades. And the interaction, right, between PKB and PKA, there's an interaction between them. You know, glycogen synthase, there's glycogen synthase kinase 3, there's PKB. So how these signaling cascades work. The key proteins in mTOR. So there's, you know, MLST8 or Gable, Raptor, and then the mTOR enzyme itself. And you could talk about, you know, Deptor, and you could talk about Pras40 as these negative regulators of mTOR. Now, rapamycin, mTOR complex 1, it's an immediate inhibitor of complex 1, but when we're looking at expression, it's a long-term, a chronic inhibitor of complex 2, but for complex 1, it is an immediate. You don't have to expose yourself to chronic rapamycin to see inhibition of complex 1. Difference between complex 1 and complex 2. There's Richter, rapamycin insensitive, but again, that's acutely insensitive. Chronically, we're seeing expression differences that will knock it out eventually. You know, PKB, SGK. You see these downstream targets are a little bit different. Interaction between complex 2 and complex 1. Downstream from complex 2 is PKB. As we know, PKB is inhibiting tuberin, and tuberin is facilitating that hydrolysis of the GTP. Big picture stuff. You know, the types of immune tissue breakdown chemicals that get released. Now, reactive oxygen species is weird, right? It's pro and anti. Wnt proteins through GSK3. Tumor necrosis factor is also a little bit weird, but interferon gamma, IL-2 and 15, prostaglandins. These things are all like pure pro. You know, the hormones that are going to do it. And you know, the mechanical sensors, those mechanotransducers, and they're sensing the different characteristics of the load. But then mechanical sensation can get clear through to mTOR even in the presence of warp-menin, because warp-menin inhibits PI3K, which is going to knock out nutrient and growth factor. But if you have if you eat a bunch of like carbs, you get all this, whether it's IGF or insulin or the some cytokines, whatever it is that's triggering it, it gets knocked out. But mechanical stimulus still gets through unless you take rapamycin. Then you're knocking out the mechanical stimulus. Now you know about mTOR and its interaction with Henneman's size principle, and this little girl in her polka dot galaxy pants, she is not contributing, so she is unlikely to benefit. And the difference between this kind of squatter and the concentration curl, what that's going to look like chemically, what that's going to look like hormonally. Now, these are some diagrams people drew on previous tests. No notes, right? It was just use your head. It's just what comes out of your head. There's no notes, and this one is good. Now, it hits all the basics. Every kind of basic requirement was met here. I don't think there's much in the way of protein, but and then this one is a little bit. It's very aesthetic. Use a ruler for those lines, and a little bit more detail, a little bit more complicated. Yuki's here. I like the color coding, right? So yeah, green is on and red is off, and over here we see the RAG GGP haste and binding to Raptor to mobilize mTOR. So she's getting into some of the nutritional stuff, and Lena Perry. This was her diagram. A lot of cell surface things that she was doing. So if these diagrams are and so here you see like leucine, LAT1, that's the transport, the RAG, GTPase, regulation. And so the RAGs for mTOR mobilization and then activation through other things. And then there's Cynthia Villalobos, there's her diagram. And she pretty much hit everything on hers. Now, these were all historically, I would just make people do this out of memory, whatever's in your head, there's no resources. And this is like, just consider, do some practices so that you know where your limitations are. If you don't get up to the plate and take some swings, you have no idea what your limitations are. So get up to the plate, take some swings, and then like, oh, I guess I don't know what's going on over here. And so here's a list of things that you're going to want to draw out, right? You're going to want to include all of these things in your diagram. And if you're like, oh, I have no idea where this goes, that's a limitation, and you should address that. You should address that limitation in your studying and go look it up. Listen through, watch the lectures again. But that's it for mTOR. That's everything that you're going to be held accountable for the upcoming test. What questions do we have?
Are all phosphorylase considered catabolic because they produce adenosine monophosphate, AMP, sorry?
So are all phosphorylase enzymes? Is that what you asked? No, it depends what you're dephosphorylating. So, if you're like dephosphorylating a catabolic thing, then that would be an anabolic. It just depends what you're doing with your phosphates. Kinases, phosphorylase enzymes. It just depends where you're moving these phosphates around. Are you attaching or removing a phosphate from something anabolic or catabolic? And but the main thing is kinase, you're phosphorylating stuff. If you activate, sometimes when you phosphorylate something, you deactivate it. But if you phosphorylate something in an activation sense, is it anabolic? Is it catabolic? Those kinases really determine a lot of your metabolism.
I have another one unrelated to that then. mTOR is translocated into the lysosome. And what happens to it there? Is it ever translocated out of the lysosome? Mm-hmm. And what process?
Yeah, it doesn't get in the lysosome. It gets to the lysosomal surface. And So again, where it is before that, I've never seen a study that says, "Oh, here it is," but it sort of just doesn't matter. It's out partying, it's having a good time. It's like, hey, you're needed at work, and like it's like a pager. You page it, and it shows up to work from wherever it is. Like, oh, I've been out drinking all night. I got to go get to the lysosome and start somewhere. I got to start working. So I'm not sure where it resides before, but it doesn't really seem to matter because its work site is at the lysosomal surface, and then once you stop the RAG signaling, mTOR goes back to its party life where it's no longer productive.
The reason that insulin kind of prevents lipolysis is because, like, if you have a high level of insulin in your bloodstream, that kind of means there's high blood sugar, right? So is it kind of telling the body to switch to burning those blood sugars as opposed to switching to burning fat?
Yes, perfect.
Okay.
Yeah, so your body is sensing. Remember, just regulation is everywhere all the time, doing its best to just tinker and make fit, both acutely fit and chronically fit. So acutely fit would be this particular situation where you have high blood sugar. Um, and your body is going to prefer carbohydrates when you give it a bunch of carbohydrates. That's both acutely and chronically. That there's going to be a preference of carbohydrates. Notice if anybody has ever spent a long time on a ketogenic diet, you don't like take naps during the day because you don't have like blood sugar doing this. You're just sort of like steady all the time. And so there's an acute effect and there's a chronic effect. And I don't know how to explain the chronic effect. I feel the chronic effect. Whenever I go back on carbohydrates, I just have to nap like during the day because you get swings in blood glucose and your body decides, oh, I'm the type of person that uses carbohydrates for fuel. But the acute effect is exactly what you said, where you have this momentary, this sort of ephemeral, fleeting, momentary increase in blood sugar and in available carbohydrates. And so the body decides, look, we have all these carbs. Let's just use this for fuel. That's what's abundant. Let's use this for fuel. And so it acutely impairs fat metabolism by activating PDE, which breaks down cyclic AMP, which prevents PKA from being activated, which prevents hormone-sensitive lipase and perilipin from being phosphorylated. So insulin inhibits fat mobilization and increases GLUT4 translocation downstream from PKB, GLUT4 translocation. Let's get those carbs into the cell. And then it also turns on glycogen synthase. So, all right, we're getting carbs into the cell and let's just like link them together and we'll store these things. And now we have carbohydrates in the bank. So exactly what you said, you have a bunch of carbohydrates and acutely short term, the body is going to respond and prefer carbohydrate metabolism, but also make the most of storage.
Okay, thank you.
Yeah.
Do you talk a little bit about lipolysis from like the triglyceride to the diacylglycerol and the monoacylglycerol or something like that?
Yeah.
The level of detail that we need to be aware of for the test and that.
Okay, so here's the extent of what I would want people to know for the test. It's triglycerides. It's glycerol, a 3-carbon thing, right? This little hunk of storage site, glycerol, and then 3 fatty acids. So there's 3 little strings of fatty acids held in place by a binder, like it's like a trapper keeper binder kind of thing, and so like like 3-hole punched paper, and it's like in the little, and I hope this analogy makes sense. Like those binders have those little 3 rings,
Yeah.
and what is going to unbind that first ring is adipose triglyceride lipase. Now, there's going to be a little bit of enzymatic swinging, let's call it, going on. But to make things clean, adipose triglyceride lipase unbinds the first one. that is now a free fatty acid. Go get oxidized. Go do your thing. You're out of here. What's going to unbind the second one in that binder is hormone-sensitive lipase. Now that's the thing. That's really what people say, like the kind of critical regulator of lipolysis, hormone-sensitive lipase. And historically, everyone just said, I mean, if you look at old textbooks, not even that old, like look at textbooks that came out like a year ago, and people still have this diagram, even though this has been known for a while to be otherwise. People just say hormone-sensitive lipase does the first two. It does TAG and DAG. Look, open up probably your 129 textbook probably says that. And that's okay, whatever, it doesn't really matter. But adipose triglyceride lipase, that's really the first binder ring. The second binder ring is hormone sensitive lipase, which we think of like PFK, phosphofructokinase, and glycolysis as like the limiting step in glycolysis is PFK. And we talked about that earlier, but hormone sensitive lipase is like that too, where it's not the first step really that's the limiting step, it's the second step. Now, if you're going from not from glucose, really the second step in glycolysis is PFK. It's the third only if you go from glucose and use hexokinase. So first ring, adipose triglyceride lipase. Second ring, hormone-sensitive lipase. Third ring, monoacylglycerol lipase. Who cares? I'm never going to talk about it. Other than that, which just I said. But PKA is going to activate lipolysis. Now it gets tricky, it gets weird with AMPK because of crosstalk between PKA and AMPK and kind of higher level regulation. But don't worry about that. So don't think about AMPK and lipolysis. Don't think about it. Just think about PKA and lipolysis. And PKA activates pyrrolipin, which is the coat around the lipid droplet, so that hormone-sensitive lipase, they can get access to the lipids. And so PKA, if active, it's going to phosphorylate hormone-sensitive lipase and pyrrolipin. And that's really what facilitates lipolysis. Now, once you have those lipids, you have to send it into once you have those free fatty acids, you have to send those into mitochondria and do beta oxidation. But that's like 129 stuff. I'm never going to talk about beta oxidation here.
Okay, so basically about lipolysis, it's all about PKA being the main like regulator, I guess.
Yes. Yeah, perfect. PKA is the main proponent, the main activator, the main regulator, the main stimulator, whatever you want to call it. PKA is really, it's when PKA is active, you're mobilizing lipids. And that's how caffeine works, right? When we were talking about methylxanthines, of which caffeine is one, and theophylline and theobromine and the stuff in tea and chocolate and coffee. These are PDE inhibitors, and so you're promoting more PKA activation with methylxanthines, like caffeine. Just who cares? You don't need to know the other ones. Just caffeine, and that's a PDE inhibitor is caffeine, and so it permits more PKA activation. So you're able to burn more fat in the presence of caffeine. So if you want to go do cardio and make it work. Right, you want to not make it work for like cardio, as in cardiovascular enhancement, but if you want to be more lipolytically active in endurance activity, then having some caffeine before is a good ergogenic aid, owing to more PKA activation. Go ahead.
That's why the fasting cardio is a thing. Like they're trying to get more PKA out of their cardio.
Yeah, if you go eat a big breakfast, or even just like, you can have fat and whatever before you do it, but if you go eat a bunch of carbohydrates and get some insulin and you're clearing the blood of your free fatty acids and it's not quite now, just like we were looking at the literature, whatever, Monday, I think, on combining aerobic and anaerobic activity. And people are like, no, it's fine. You can totally do it. Look at the literature. Yeah, well, I did. That's why I have a problem with combining the two. A, physiology says you shouldn't, and B, the literature does not, contest that. But it's similar here, where when you look at the literature of people who say fasted cardio, unfasted cardio, eat beforehand, or if it's all the same, we're missing the literature is bad. The way they're doing the studies is not particularly effective. And you can even get to the point where I may have mentioned this at some point, where people talk about the intensity, and everybody just wants to be a contrarian. Everybody wants to say something that's opposite of conventional wisdom. So they have, just like when Jacob was asking about the person, or somebody, I think it was Jacob, asking about the person who like does 20 or 30 reps or whatever, like where does hypertrophy live? Jacob, was that you asking about? Okay. People just like to have contrary statements, and so when you see things like feel free to eat before exercise, or you just, that's not really, it's more complicated than this, or than one particular study that was poorly done. And so I would say physiologically there's evidence that fasted cardio is of value. Now, what is the discrepancy between fasted cardio and well-fed cardio? What is the discrepancy over the course of, do it for a month, and what is the difference? I don't know. But there's sufficient evidence that fasted cardio is going to work better. In part, it's going to be the insulin. Now, you'll clear insulin. You go into cardio and you'll start clearing your insulin. Yeah, you're not going to just maintain a bunch of insulin blocking lipolysis. As you exercise, you'll start clearing insulin. You'll start seeing your epinephrine increasing, and moving into that optimal space for fat mobilization. But people also talk about the heart rate, and they say, oh, fat burning zone, that's fake. Well, hold on, not really. It's as a matter of magnitude. It's like saying global warming, that's a hoax. Like, well, hold on, what are you talking about? So people just like to be contrarian about stuff. And fat burning zone, yeah, maybe people talk about fat burning zone in sort of a silly way. But if you get too high in intensity, you look at the actual release of free fatty acids from cells go down. So there's the you increase and increase and increase and increase in intensity, you're just burning more and more and more and more calories. You max out your total fat metabolism, and now the rest of it is just carbohydrates on top of that. Yeah. And then this happens as you increase intensity further, and compensate even more, because you're just not releasing it. Now, whether that's like the blood is rushing by and you can't drop your kids off at the school going 40 miles an hour. No, tuck and roll, get out of the car. Like sometimes there's a matter of blood kinetics that affect these things. But after cardio, intense cardio, sometimes you'll see this excess release of free fatty acids, because we went through a bunch of lipolysis and we couldn't use anything, and so it was all carbs during, and we'll burn some carbs after. So it gets a little bit more complicated. But this is where physiology starts to tread into opinion. Fasted cardio, a little bit more effective. Fat burning zone, a little bit more effective. Like these things, a little. Now, what's the magnitude of that? I don't know. I don't have any commentary on the magnitude, but there's physiological justification that is sound for these things, that is supported in the literature, and is physiologically sound. And people who say like, oh, that's dumb, that doesn't work, that's just someone trying to be contrarian, who doesn't have a comprehensive understanding of the literature or the underlying biochemistry involved. And my support for these things, I'm not saying is absolute. 20 years later, when we have more physiological understanding of how these things work, regulators of adipose triglyceride lipase under particular conditions, that yeah, maybe there's more to it, but it seems like some of these things do have value. I'm obviously not going to ask that on a test.
So it's basically not like an absolute, just that in certain scenarios, like if someone has insulin sensitivity or something, would that be a case where fasted cardio would be more beneficial, and like insulin sensitivity type stuff?
But if somebody has reduced
Something like the
insulin.
blood sugar effect of cardio.
Yeah, if somebody has poor insulin sensitivity, I would say exercise after meals. Just like you don't want to rely on insulin to get that sugar into the cell. So as soon as your meal is over, don't even do the dishes. Just go for the walk. Go for the do whatever. Now I wouldn't go do something intense for a couple of seconds because you get this hepatic glucose production. Like, oh, let me go do like one set of all-out pull-ups, or like, okay, well now your blood sugar is like even higher than it was before because the liver was anticipating this big endeavor, and so you're like dumping carbs into the like. So now I don't know how much. Relative responses of what somebody just ate and how intensely they're working and that particular person's physiology. But yeah, just put down the dish. If somebody has insulin sensitivity complications, I just put down the fork when you're done eating. Go eat your pasta or whatever. Put down the fork and then just go for a walk. Allow AMPK to a brisk walk, whatever. It depends on the person's fitness level. Allow AMPK to do insulin's job because it's going to do it way better than insulin. AMPK is better than insulin at glucose regulation. But so it's a person by person scenario. The circumstances, it's hard for me to say without knowing the person's history, what is this person's fasted blood sugar and what is their cardiovascular history, not just like adverse events, but history of training and resting heart rate. And it's hard for me to have prescriptions without knowing the details of a person. I don't know if I answered your question at all.
Yeah, that was a pretty good answer. I was just wondering about the fasted cardio because it seems like a lot of people are doing it to lose weight, and I was thinking in my head that it would be effective as that, just because like you don't have any glucose.
Fasted cardio I understand what people say. Just like when people say you run the mile. And do you walk the mile? I mean, you do the math, right? And I've watched people do the math. I sort of roll my eyes. People are like, no, you walk the mile or you just all out run the mile and you burn the same amount of calories. These are the sort of cliches, the physiological cliches that I hear. And I think, okay, we have some fundamental flaws in how people are doing this. Yeah, okay. When you look at met values, what a met value of 3 means like you're 3 times your resting metabolism. A met value of 4, you're 4 times your resting metabolism. Metabolic equivalent of the task. And if you're walking, your met value is lower, but it takes you longer to cover a mile. If you're running, your met value is really high, but you don't exercise for as long. And so people are like, yeah, you cross the finish line, it's the same number of calories. No, that's not really how it works, because let's look at more longer term stuff, the inflammatory markers, the tissue damage. You have to pay for this stuff. Protein translation is really expensive. The hour later, your heart has beat, once you've crossed the finish line, and then an hour from now you have more heartbeats in the person who ran the mile. And so there's so many other variables to consider rather than just how many calories did you burn when you crossed the finish line. Okay, it's just so crude, right? It's just so sort of, the math is just way too simple. And so people don't always consider all of the inputs, all of the variables when they make these very simple, intuitive claims. And so I hear these criticisms of a lot of physiological practices, and but there's sound evidence or justification. It's a little bit more delicate.
Basically, it all depends on the athlete and the time of the year and what kind of goals they have.
All of that stuff. It depends on all that stuff. And, task analysis, athlete history, the individuation component. I think it was like lecture 1 or something. We talked about individuation. A person is not a person. A body is not a body. An athlete is not an athlete. Everybody is different in terms of their training and their resting hormone levels, fasted hormone levels, and some people have more growth hormone or more or less testosterone, and some people. It's just, there's so many differences in bodies, and we don't all respond to everything in the same way. And so simplifying, one of the things that always irritates me is, and I've just sort of, I can only sigh so much when people think that like exercise physiology is just simple. Like, oh, it's just push-ups. And like, what the fuck are you talking about? Like, um, and
squat, bench, deadlift.
yeah, so people don't understand the complexity that's involved, and I think every field has a lot of complexity in whatever. I mean, just like in our last lecture, I was talking about sort of all the literary stuff, and so people think what writing is. I'm like, no, that's not writing. Like writing is the ridiculously complex. It's probably the single most complex task a human being is capable of. And I say that with evidence of some reasonable justification that there's very little, verbs that compare with writing in terms of the complexity of it. But people think like, oh, it's words on a page, that's writing. Like, and it's the same thing with sort of exercise physiology, and people like, oh no, I ran and I crossed the finish line, and here are my calories. Like, that's not how the body works. We really have to start with like cell signaling and basic metabolism, and to understand these things. And so the metabolic activity of whether it's a fat cell and it's releasing adiponectin and it's releasing leptin, and so even just like the release, what a fat cell is doing in these different, whether you're fasted or having dined, what is the condition of the release of things like adiponectin and leptin, and where are you physiologically? Let's sample your blood, whether you're fat. It's not just like how many calories did you burn. I mean, that's like so stupid. But that's sort of what people think with exercise physiology is like, oh, mets and you burn calories. Like, oh, okay, that's not even, that's like 3 days into 129. Like, what are you talking about? Everyone sort of thinks because they have a body, they're an expert in bodies. Oh, I jogged once. I think it was in this class, or maybe it was 180. I don't know, where I talk about Ben Tollerene, the poker player, and how he just refuses to tell people what he does for a living because everyone thinks they're an expert in poker. I mean, he makes millions of dollars every year playing poker, and he's world class. He's like one of the best ever. And I mean, that guy is so smart. He's like stunningly smart, not just in poker, but when people ask him what he does for a living, he never says poker, because it's like, oh, I'm really good at poker too. Like, you have no idea what you're talking about. And so I think it's a similar phenomenon in exercise physiology, where people have a history of exercise, so they think they're experts in physiology, when everyone here knows how complex this stuff gets, how circumstantial and complex every cell behaves totally differently based on different circumstances.
Why the really good strength coaches make a lot of money and most of them don't make very much.
It's uncommon to have intelligence as foundational in a lot of sport jobs. Mostly what it is I'm an ex-player. I was good. Okay, I don't care if you were good. What I care about is, do you express talent in making other people good? Do you know how to enhance skill, enhance capacity, enhance physical functioning in others? That's what coaching is. It's not like, look how good I used to be. Who cares? That's not interesting. And so
players actually get better when they leave 4 years from now or whatever.
You find it's sad.
I noticed that so much at Pacific when I was there. It was like the pitchers would come there. They were pretty good. I was pretty good out of high school, and then within like a year or two, it's like your velocity's gone down by like 2 or 3 miles an hour. Or your arms hurting every day.
So once in a while, you'll encounter a coach who has like a doctorate in physiology or biomechanics or something, and oh wow, I'm so surprised how successful you were. And then they like to hire the ex-player for a ton of money who has never taken a science class, and like, why? What do we expect? You're gonna lose every game. That's how it works. And so at some point, I think science will overtake history of performance. But we're not there yet.
Yeah, I had a pitching coach who had a degree in biomechanics, and he was amazing. But then, I had one of my college strength coaches at the NAIA school I was at, and he had a business degree, and he literally didn't know anything about physiology. I knew way more about physiology than he did, but yet he would make these really bold claims about how to prevent pitching injuries and stuff, and how pitchers should condition. I was just like, okay, you don't have any idea what you're talking about. Like, I'm
This is
just gonna tell everyone on my team that they need to do these things that are actually gonna make them better and not to listen to you. Like,
This is when people make really bold claims. That's usually, not always, but usually an indicator that maybe they don't know what they're talking about. Even just when I was just like 5 minutes ago, when I was talking about fasted cardio or the fat burning zone, or the intensity, or what you're eating, these different variables that relate to the success in weight loss. I was saying, like, the state of evidence. These are complicated phenomena, and it's not a crude calculation, and there's enough evidence to support it. But in 20 years, is something new going to come out? Like, I sort of hedge all of my claims. If there's something where the science hasn't really settled, I'm going to be cautious in how bold I am. Now, if it's something that's like, okay, this is just how it works. If it is size principle, I'm willing to be a little bit more bold. But even when I'm talking about size principle, I mean, this thing that's been studied since 1938, and it hasn't really been overturned. And Henneman came along in 57 and kind of added his neuronal component and even then, I said, like, it's possible that we're going to see some evidence of some contrary evidence, but what seems likely, even there, I sort of build up some caveats. There's a lack of boldness, because you don't want to say something that turns out to be incorrect next year. And the people who are a little bit more oblivious to physiology, its history, its current status, and its likely future, make the boldest claims. Coaches and strength coaches often make ridiculously bold claims when it's like, there's not really much to support that.
Yeah, the science takes a lot longer to catch up to, like, the gym science, I guess. Like, what people have been doing for years already. The science takes longer to catch up to support.
Yeah, real science takes a long time. Now, that's not to take anything away from gym science, from the perspective of there's like the bro science or gym science, or a lot of that's right, not all of it. A lot of it's also wrong. In the 80s, they start like doing all this testing of that stuff. The NSCA, Journal of Strength Conditioning Research. You see a lot of studies coming out, 80s and early 90s, that are testing some of those gym science claims, and like a lot of it was just like, okay, this is like the opposite of the truth. But there's a lot of that that is true. It's like one of the things I was talking about on Monday, or maybe it was last week or something, about why are the bodybuilders, why is the Ronnie Coleman's of the world, they're eating like an absurd amount. They're eating like a pound of protein every day, and the nutritionist is saying, no, 70 grams will suffice. More than that relative to like a bodybuilder's body weight. But there's rationality. The gym science was sort of ahead, because nobody knew mTOR signaling and translocation of mTOR to the lysosome. People didn't know any of that stuff. I mean, that's all really recent. But the bodybuilders were taking advantage of this and just introducing all of this protein all the time so that mTOR can be active of how the cells. Do you need all of that protein? Well, no, but can I get some mTOR translocation by eating more? Well, yeah. But the bodybuilders have no idea. But the gym science is ahead of kind of nutritionist studies. And I'm not saying that's healthful or whatever, but gym science there is something to that, like, tried and true method of X, of whatever it is, where like people have tried a bunch of techniques, and this just is the thing we have to do because everyone does it who wins. Okay, we'll test this, and over the years, maybe we'll figure out why everyone's doing this. And so there's something to be said, something positive to be said for gym science, but there's also negative stuff to be said about it.
Not all bad. It's kind of what you're saying.
It's not all bad. Yeah, some of it's bad, but it's not all bad. It's just it's stated with such bold authority, and that's often what the problem is.
Interesting.
Other commentary, questions?
I mean, I had one, but Yeah, this is kind of off topic, and I didn't, and you don't have to make this a long answer in the sense of like I know that you're busy, I know we're all busy, and it's 4, but just out of pure curiosity, um, Professor Chicolella has stated that she thinks that in the future, regardless of what occupation we get in this field, our biggest conflict or thing we have to overcome is all of this abuse of false information, lack of knowledge, kind of what you stated, and mainly just what she said is the abuse. Like, I mean, you talked about this earlier in the year that you can get certified as a personal trainer and take like a dumb course online with 60 questions, with, that are super easy. I guess what I'm trying to ask is, given social media, given how our generation is becoming a lot more global and I guess a lot more accessible and in the moment. I mean, we can get the news right now. I can just look it up, like look up COVID news and COVID statistics. I guess what I'm trying to ask is, how do you think, our jobs, again, it's a very broad question because our jobs will differ, but in this kind of field with HESP, with muscle physiology, with, even being a PA, stuff like that, what do you think our biggest conflict, given our generation's new technologies, will be to overcome?
I like what Peg said there. We have this collapse of trust in institutions, and I'm going to answer this question in a slightly different way because that's what I do. When I go to Uganda, there's no respect for institutions. Watch people drive in Uganda. It's hilarious. It doesn't matter what side of the road you're on. Lights exist. There's a such thing as red and green, but they don't mean anything because there's no respect for institutions. And so even like stepping off an elevator, nobody waits until you get off, and then you just like do this like you bumping into me. It's like you're like in a mosh pit in like a 1992 concert, and we're getting to that point in the US where there's this collapse of respect and trust in institutions. And we see that with things like COVID or, people are the doubting of climate scientists and so the villainization of the American Medical Association, which in part there's component sometimes people have a point in these things. Now it's not what Twitter says, but or what is popularly shared on Twitter is what I mean. But yeah, as these trust in institutional claims, when the CDC makes a claim, the NIH when they make a claim, and people are like, oh, it's just a bunch of bureaucracy and it's bias and it's whatever. Like, okay, well, these are like the world experts in the entire world. These are the top experts in this field. There's no more equipped person alive who can answer this question than the person who just gave the best answer they could. And immediately, people like high schoolers are saying that person's an idiot. And so I think that is going to play into your job and your career, where you're going to be like, well, let's talk about this scientifically. Oh, that's all corrupt. Fine, just follow the dollar. And people will just like, well, no, this is, let's that's not how this works. Like people don't have an understanding of the nature of science. And I think it matters. And you probably will have what Peg said. I think you probably will encounter some of that. Distrust in science, and I don't know what a good solution is, but all I can do is sort of agree with Peg and add my peripheral commentary to it.
I did have a question. Sorry, you just thinking about different things. Arachidonic acid, you said, does have an effect on hypertrophy, correct?
Yes.
Okay. So then would combat sport athletes have a greater ability of hypertrophy because of their arachidonic acid being released from the contact?
That's a really good question. I don't have an answer, but let's go back to the idea of contact adaptation. maybe that's a part of it. Maybe that's sort of the chemical trigger of contact adaptation. I don't know that. I don't know that that's the answer, but it's worth contemplating that you're going to have a lot of disruption. When you have tissue disruption, you get those interleukins and prostaglandins, and so you're going to get all of this chemical signature of tissue disruption. But specificity of adaptation, what was the loading profile? Where was this like an impact? Okay, how do we reinforce the matrix? How do we reinforce the tissue so that it can withstand future bouts of impact? So and so maybe but I don't think getting punched in the biceps is gonna like you're doing bicep curls and like, okay, I'm doing the negative, punch me, all right, keep going, keep punch. I don't think that's, maybe it does. I don't know, but I don't think owing to how precise mechanical signaling is, how specific specificity of adaptation is, I have my doubts that the contact itself is going to introduce more actin and myosin as opposed to more whatever structural proteins or reinforcing the tissue to withstand that particular stress is a really good question. And I'm sure that chemical profile contributes to the adaptation, but in what way is it contributing? What is the nature of the adaptation and the time course of the adaptation? I really don't know.
Yeah, I didn't know if it was going to be localized or if like the arachidonic acid would just like enter systemic circulation.
I like that.
And then so like after a day of sparring, the next 2 days their mTOR signaling might be a little bit elevated, so they'll reap slightly better benefits.
Yeah, that's believable to me. Yeah, to me, I'm willing to, if that's the first blush, I'll go, oh, I like that hue. There's no immediate reason that comes to mind for me to poo-poo it, right? It seems there's a logic to it. Anything else or anyone else? All right, I will see everybody. mTOR over.